Hello everyone, welcome to my talk. Today I am going to talk about the beginner's guide to the Flink SQL query optimizations. And let's get started. I was in this room I saw the early morning talks. I hope I can set the bar. They were really nice. Okay, short introduction about myself. I am Muhammet. I work at Fairworker. I am in the engine team. We mainly implement, maintain Fairworker engines, Vera, VeraX, for our different products, BYOC, cloud offering, and on-premise offering. So this will be a short agenda for today. After introduction, I will go directly into explaining Flink SQL optimizations. Optimization, in a sense, which happens on the planner. And then I will show some examples which are generated by the optimizer and planner. And if we have time, hopefully we have, we will debug one issue from the open source Apache Flink. Then I will conclude the presentation and answer your questions. Because of the 30-minute time, I had to remove some slides which sets the context or explains some terms. If you have any questions, just let me know and I can explain it. So let's look into the life cycle of the Flink SQL query, starting once the engine receives the SQL statement, it parses it into so-called SQL node. Then using the parser, then the main job of the engine is to convert that text into the abstract syntax tree, which in the end will be converted into the logical plan. Here also the parser will gather all the information about the metadata, catalogs, validate the tables, columns, types, and UDFs, and so on. After the validation, the abstract syntax array is converted into the logical plan, which is the input into the optimizer. And optimizer will run many steps, which will generate efficient, optimized physical plan and execution plan. But we are not done yet. Many translations will be applied to the execution plan to create a stream or batch low-level operators that in the end will be converted to the job graph and will be submitted to the task managers for the execution. So many steps are involved, as you can see, and today we mainly look into the optimizer in detail. Before moving forward, I want to explain or define what's a relational tree representation. So given a SQL query, it's first parsed into the abstract syntax tree. It's a complex tree structure where, for example, given a select has a child nodes for the join, group by, where, close, and so on. The AST models syntactic structure, but not the relational semantics. It's hard to map some of the optimization rewrites transformations on the abstract syntax tree. For example, you cannot easily express what will be the join. Will it be merge join, hash join in the AST syntax? For that reason, some other internal representation is required, which is called relational operator, relational node, or relational tree. There are huge research on that in the database. So once we have a relational representation, we can define the common operators, such as join, aggregate, table scan, filter, project, and so on. And queries represented in these operators are easier to optimize because they have well-defined scope usually with one input. And one other good thing with the relational operators is you can apply relational algebra rules. For example, you can transform them using commutative rule, transitive rule, or distribution rule. Okay, let's jump into the Flink SQL optimizations. So the Flink SQL optimizer is based on the Apache calcite optimizer, and this is a kind of high-level overview for all the optimization steps. Once we have the logical plan, it's input to the optimizer, which goes over many rewrite rules. So logical plan will be transformed, rewritten, or reordered based on some rules. And finally, it will convert into the Flink physical plan that again goes through many rewrite rules and the cost-based optimization steps. Here, optimizer will use many information, metadata information, for example, from the Flink SQL Flink configurations, hints from SQL statements, catalog metadata, statistics for the batch jobs, and so on. So we can look into the rewrite rules. It's one of the most powerful features which are coming from the Apache Calcite optimizer. The idea here is to look for a pattern. Once the pattern is matched, we can rewrite it in a different way. For example, we have here a plan, aggregate happens after the join. After scanning, we have a join and then aggregate. We can match the aggregate and the join pattern and rewrite it into a different format where the aggregate is pushed down the join. And the name of this rule, which comes from the Calcite project, it's an aggregate join transpose rule. And the idea here is we want to decrease the number of data coming into the join. Of course, Calcite have many rules by default out of the box, but sometimes we need to adapt it or modify it to fit to the Flink SQL. For example, here, aggregate join transpose rule is modified because we don't want to match it on lookup joins. Yeah, as I said, Apache Calcite comes with many rewrite tools out of box, more than 100. And there are some of them, for example, we can simplify expressions. If you have 2 plus 2 in your where clause or filter clause, we can just evaluate it, and we don't have to do it at the runtime. Or if you have a function which has with arguments which are only the literal values, you can just evaluate the function and substitute it in this planning phase, and you don't have to evaluate it at the runtime. And there are many complex rules also. For example, rewriting the subqueries to join. If the query contains exist or in, you can rewrite them to the join. And in the rewrite step, you also do initial filter pushdown if there is a where clause in your queries. I want to talk about the cost-based optimizations, which is also based on the Apache Calcite project with the so-called Volcano Planner. It's a Volcano is, you can find it in research, one of the early planning or optimizing papers. In this case, we don't consider only one single plan, but instead try to consider multiple plans at once. And the idea is we start from some root plan and try to traverse all possible rewrite rules and select the best possible plan. So here we also generate so-called equivalence groups. For example, for the E4, that's an equivalence group. If you follow both the ways, aggregate way or project way, you will get the same results. That's why they are collected into the same equivalence group. But with the cost-based optimization, what does the best plan mean? Here, we also need to define like a cost for each of the operators. And each operator defines its own cost, which are based on some information, such as I/O, network, number of rows. And the cost is calculated also including the child. And if the cost is available, now we don't have to, once we find the best plan at some of the operators, we can store it and store it in a cache. So whenever we come from the another path into that operator, we can just fetch it from the cache, so we don't have to explore it furthermore. So the idea is here to apply the dynamic programming with a cache or a memo data structure to reduce time to search for the best plan. And there are also some specific optimization rules which are only valid for the Flink SQL. For example, watermarks is available only in Flink, so we need to, unlike in a data stream API, we don't have a window assigner class or API. So whenever you define a watermark for a column, the planner needs to push the watermark into the table scan. And many other rewrite rules which are specific to the Flink, for example, Python calls or the async calls. And also, for example, if you have an over window, you can convert it into the top N operation, or something specific to the Flink, the changelog modes. For example, you can planner needs to sometimes infer if the changelog mode should stay in initial append or observe mode, or should it also include the retraction mode, because when you do the computation, if the value changes, you want to remove it, send the update before record to remove the previous value from the computation. Okay, so what are the final outcome of the optimizer in a Flink SQL? It's to create an efficient physical plan. Once the efficient physical plan is found, it's converted into so-called, each physical plan node converts into so-called stream exec nodes. Stream for the specific to the streaming case, but it's also valid for the batch. There are corresponding batch, for example, batch exec calc class are also available. So this is a final outcome of the optimizer and planner, and these exec nodes can be converted into JSON, serialized into JSON, and also visualized in the UI. But afterwards, once the physical plan is defined, they are also transformed into the low-level Flink operators to generate the job graph, which will later we submit to the runtime. Also here, another concept is code generation. So imagine you have a SQL query where you do the filter or select. Those needs to be generated into the code from the SQL strings, in this case for the Java code, which will be then applied on a data. Okay, let's look into some examples. So let's imagine we have a table we define, which also supports filter pushdown on the left, and we run a select query on top of it. Then the generated plan will be something like this. So we have here the relational tree. Going from bottom to up, we have the table scan, the filter condition for both of the expression, and the projection. And since the table supports filter pushdown, as you can see on optimized plan, the filter is sent to the table. So the table scan will give you data already filtered out. You can check the documentation to see how to run the explain queries. There are many options, for example, with the detail, with the changelog mode invert, show the plan, and etc. It helps sometimes to debug if you have issue in your Flink SQL queries. Another example is a watermark. So now on a table, we define a watermark for a column. And here, additional logical plan is set after the table scan watermark assigner, and watermark is also pushed in the optimized physical plan into the table source. Because watermarks have some special constraints, because once you define a watermark for a column, you cannot update, users cannot update that or change that column. It should be in sync with the watermark system of the Flink runtime. Okay, here another interesting thing is that the table now only supports partial pushdown. You can only push down the name column, but not the age column. And as usual, we have the similar relational plan, but here the filter only for the name is pushed down to the table source, but then afterwards we have another calc mainly operator for doing the filtering and the projection. We have additional workflows for age, which filters the data again. Okay, an example for projection, it's similar to the others, but here the calc only selects one column instead of the star as previously, or all the columns. Yeah. And some complex example, we have the CDC source, and I think here I wanted to show the two-phase aggregate. For example, the optimized plan have two aggregates, the local window aggregate and the global window aggregate. And another interesting thing is you can also see the changelog mode. So this was run with the explained plan with the changelog mode enabled. Yeah. So, yeah. I want to continue, and it's also why I have this talk initially. I was looking into a bug which came from our customer success team. The June reported this bug. You can check the links if you're interested to read it. There were many iterations. Finally, I looked into this. And let me explain it. So we have two tables here. Doesn't matter what is the table. Basically, we have a large data set, imagine it. So in this table, we have two records with the ID, Alice, and the Bob. And we have some smaller table with a, let's call it a dimension table. Again, we have ID and status. And the idea is we have such a, I'm not sure if you can see it, a query with the union. And we want to join our stream table with the dimension table on a processing time, but the dimension table needs to be filtered first, which we are only interested on the records which match this status OK. So in a table, we have only two records. And at the same time, we have the same query for the second part of the union. But now the filter condition is something dummy. It doesn't exist in a table, in a dimension table. So when you run this query in the Apache Flink, you will get a result something like this, which is totally wrong. Where does the not exist come from? It doesn't even exist in my table. So the expected output should be something like these two rows, where the status is matched as OK. So initially, we thought it was something related to maybe the JDBC connector, because JDBC connector also does a filter pushdown, or something related at runtime. But in the end, it ended up to be the issue in the optimizer and the planner. So to debug this, I, of course, started with generating the plan. And looking into the plan, it looks OK for me. Like here, we have the union, as expected, and the two parts for the union. So the first one, we have the filter for the OK case, then the logical correlate, which will be in the end converted into the lookup join, and the same for the other part of the union. So we have the filter for some dummy value of the status, and again, reading the dimension table, the stream table, and then they will be correlated or joined using the lookup join. Looking into the plan, it looks all right. The optimized plan, same again. So we have the union with two parts, where the logical correlate is converted now into the lookup join. And yeah, same for the other part of the query. And then we just select the columns, right? does anyone know where could be the bug at this moment? OK, so that's the optimized plan. Let's continue. And I didn't know what was happening, and I had to log every step of the optimizer, what was happening as input comes and output comes. So this is one of the logical rewrite rules. So looks similar to the plan. So we have the union, and again, two parts for the union. Here we have the select, a logical join with the stream and dimension table, and then, selection for the cat. This is fine, and as you can see, this input here, the logical calc, has a filter query for the table. And what it does is the output, this is a filter pushdown, basically, is pushed into the table source scan. So for the both OK and not exist strings, which is fine. We want the filter pushdown, and the JDBC supports filter pushdown. We want them already filtered out in the table. Then, again, the same input, output of filter pushdown, is given into the physical optimizer. Now, this one is a cost-based optimizer, and you can think how the cost-based optimizer works. If you remember the caching and etc. So here we just convert the parts into the logical join. So, OK, I have the join here. I convert it into the logical join. And then I have the calc operator. For this one, it's OK. Status will be OK. For that one, the status will be not exist. And this is fine because already logical join considers that the dimension table is filtered out, right? The filter is pushed down to the table source scan. And still, it looks good. Everything looks good by the planner and optimizer, but opening the debugger and doing some adding the breakpoints, you can see that we have the logical union class, and I'm not sure if it is visible. This is a logical join. This is the other part of the logical join, but these highlighted parts are exactly the same. So that's a bug, right? So somehow this, this shouldn't be. I would expect that this is for OK with the OK filter condition, and this one is with the not exist filter condition, but they are exactly the same. And now maybe you can guess what happens here. So when doing the cost-based optimizer, the optimizer reaches the first part of the lookup join with the filter OK, and it generates the best plan for it. It stores in a cache, and then while looking for the other plans or traversing other plans, we came to the second part of the union, and there somehow the optimizer selects. So I saw this lookup join. I have the best plan for it, and let's just fetch it from the cache. So that's what was happening here. But again, the question is, why we have this not exist in the result? Where does that come from? Then we are in the codegen part. So we have the lookup join, and then we have the calc operator just after the lookup join. So what happens here, we have, for example, the planner selects this lookup join, which is the records with the OK status. Same for this one. But if you look the calc operator, it overwrites the status. So we have the OK for this part, but again, with the lookup join here, also the OKs are coming, but the calc operator later overwrites that with the not exist. And of course, if you can debug it, you can see something like it's a Java generated by the Java. It's not very, but if you remove other parts, you will see something like this. The code gen for this calc operator will be something. Okay, we have some constant string, and then somewhere in this process element, it sets the output of for the status to that constant string. So that was the reason why we had this bug. And the pull request is also available, already reviewed. I have addressed the reviewer's request. The idea in the end was, OK, for the physical lookup join, also include into the class definition the filter pushdowns. So in that case, the two parts which we had, the OK filter or the not OK, will be totally different, and the optimizer will not select the same same best plan which it found in the initial part. Okay, that's a conclusion. We learned about it was a journey for me to debug this. I learned everything by debugging this bug. We learned, I hope you also learned about SQL optimizations, rule-based, cost-based optimizations, and yeah, we debugged the bug. Thank you, and if you have a question, I am happy to answer them.
Thank you. Do you read the execution plan, the physical plan, everything when you debug locally, like from the IDE? Or do you print it on a Flink session cluster, or in, how do you iterate?
For this, I started, initially we thought the issue is maybe in the JDBC connector. Qingsheng also did some initial investigation. Then we didn't know why it's happening. So the idea was, OK, maybe the filter pushdown is not correct. Let's print the plan. And from the, as you see, planning, everything looked OK. But we didn't know what was happening. And then we had to enable the logging to, for example, if you enable in the local, in Apache Flink, to the debug mode, you can see what optimizer does in each step. So it also prints many information about what is being as an input, the output. Yeah, and then at some point I had to set breakpoints. One other story I wanted to, so this was reproducible with the JDBC connector. And at some point, what happens with the tests? Let's look into the tests in the Flink project. And there is a test for using the values connector, which is provided for the testing only. And if you enable the filter pushdown for the values, you will get the same result. So that was good for us. We know now we can reproduce it in a test, and then we debug it from there. Great, thank you.